All right, number 6 on the exam. Says if cotangent theta equals 2 and theta is in quadrant 3, find the other trig functions. This is actually, I think, a fairly difficult problem because when you're given one trig function in a quadrant, you can always solve it, but the tangent and the cotangent are the hard cases. Probably cotangent is hardest of all. There's more than one way you can do it, but I like to do it this way. Cotangent theta equals 2 can also be written as 2 over 1, right? And now if you divide this top and bottom by the root sum square of those numbers, 2 squared plus 1 squared square root is square root 5. Write it as 2 over square root 5 over 1 over square root 5. Or you can take minus the top over minus the bottom. These are all the possible sines and cosines you can have. Starting to look from there. So this could be y and this could be x on the unit circle. Or this could be y and this could be x on the unit circle, which makes them also the sine and the cosine. Oops, I'm sorry, it's cotangent. Cotangent is x over y, so this would be x and this would be y. X and y. So which is it? Well, it has to be quadrant 3 where they're both negative, right? So we throw this one out and say this one is quadrant 3. That's the big step, is to divide them to each by the root sum square. This forces them to lie on the unit circle. What you're doing is you're saying essentially the cotangent x to y is 2 to 1. So here's a point on the terminal ray, 2, 1. Terminal line. But actually we want the angle that's on the unit circle that corresponds to that and is in quadrant 3, and that's over here. Minus 2 over square root 5 minus 1 over square root 5. This will have the same cotangent on either side. Remember, opposite directions have the same tangent and cotangent, but it's on the unit circle in the right quadrant. That's the way to think of it, is divide by the root sum square, so it's on the unit circle. Pick the one that's in quadrant 3 by choosing the negatives. And now you've got it. This one is automatically the cosine of theta. And this one is the sine of theta. And that gives you all 6 of them. So cosine, sine minus 2 over square root 5 is the x, minus 1 over square root 5 is the y coordinate. Cosine minus 2 over square root 5 is the x coordinate. Tangent is y over x. You could get that easily just by taking the reciprocal of cotangent 2 is 1 over 2. Cotangent was given. And then the cosecant is the reciprocal of sine is minus square root 5. This one you just put in the y coordinate, this one you put in the x coordinate. And then secant is the reciprocal of this one. It's minus square root 5 over 2. So that was that one. That was one of the harder ones. Any others we should look at? Yeah.
Number 4.
Okay. This is the time I think we usually learn more than most times, because once you have a little understanding, then it sinks in better, I think. Let's see. So number 4 says this. This is the one of the other 3 cases I gave you. I said if it's a special angle, or if I give you one trig function in a quadrant, or if I give you a point on the terminal ray, you want to be able to find all 6 trig functions. Remember those 3 cases? So if the terminal ray for theta contains the point 9 minus 12, find all 6 trig functions values for that angle. This one is somewhat the same, right? You want to find the corresponding point on the unit circle. I like to picture this in my head, so I'll draw it for you. I go 9 out here, minus 12 down. Sometimes that picture helps you to make sure it's in the right quadrant, but the idea is here's the terminal ray. And whatever point, angle I pick for theta to make that the terminal ray, it could go this way or this way, it doesn't matter. I want to find what are the 6 trig values. I can think of, well, if I was on a unit circle and pick this x and y, I could get them all, right? But the way to get that is to just figure that you divide through by the root sum square. The idea is that this point is on a big unit circle whose radius is, right, from this triangle, the root sum square of 9 and 12, right? Minus 12. 144 and 1. $225, so you got square root 225 is 15, right? So this side is 15 of the triangle, that makes the radius 15. What we want is the point on the unit circle. We just need to divide that by 15 to get the point on the circle of radius 1. So also, divide this by 15, 9/15 minus 12/15 is in the same direction on the unit circle. That's your x and y. But we can reduce these. I want you to reduce them whenever you can. This is 3/5 and minus 4/5. Once I know that's the x and y, I've got it immediately, right? Sine is the y coordinate, minus 4/5. Cosine is the x coordinate, 3/5. Tangent, see how it all looks easier once you've done this? Tangent theta is then the quotient of those, y over x. The 5's cancel and you get minus 4/3. Cotangent theta is then its reciprocal. 3/4. Oops. Secant is the reciprocal. Cosine is 5/3. Just turn all these things upside down. And cosecant minus 5/4. This one upside down. So that was that one. Yeah.
So the square root of 225 is 15. What does that represent?
That represents the radius of this circle. If you take the terminal ray out to here and say this point is on a terminal ray, you can think of a circle of radius 15. You get it by this right triangle here, 9 by 12 by 15. And the idea is that if you want the corresponding point in the same direction on the unit circle, you just take the circle of radius 1/15, this one, so you divide those numbers by 15, you get the point on the unit circle. So it's a scaling factor to divide these to put it on the unit circle and get x and y. But it's this side of the right triangle, it's 9 by minus 12.
Could you do number 13?
Okay. I have posted the key online, by the way, too, so if anything right on the board isn't real clear, you can always look on there too and ask me. It's at 13, right?
Yes.
Oh, okay. This one I think I should have spent more time on. It was supposed to be an easy one, actually. Fill in using the cofunction identity. Problem is, I did this at the end of class when everybody's asleep usually. Cosecant, I can never do these hour and 15-minute classes. Nobody can stay awake the last 15 minutes. Cosecant, 55 degrees is equal to the secant of how many degrees? Obviously, it's still in the blank. And the thing to remember is the cofunction identities say that the cosine of any angle, sine of that angle, sine of 90 degrees minus that angle. The cotangent of any angle, tangent is cofunction of 90 minus theta, and the cosecant of any angle is the secant of 90 minus the angle. And this just comes out of the little triangle. If you make a triangle, it also holds for any angle, but it's easiest to prove with the triangle. If this is theta, then this one, so if they add up to 180, must be 90 minus theta. And we said you just label these however you want, A, B, and C. For instance, the cosine of the angle is B over C. So this, but that's the opposite over hypotenuse for 90 minus theta. So it's the sine. That's how you prove it. You just look at the for acute angles. You just look at the little triangle and you get all these, and then if you forget which way is which, it doesn't matter because the opposite order holds with each cofunction. So sine with cosine holds the other way too. Sine of theta is cosine of 90 minus theta, etc. Tangent is cotangent 90 minus theta. And secant is cosecant 90 minus theta. So they go both ways. So on this one, all I wanted to do is take 90 minus 55. It's 35 degrees. Long answer, but I just thought I needed to maybe mention that again because a lot of people miss this one. Anything else? Yeah.
2, please.
Yeah. Okay, yeah. Number 2. One of the troubles with this one is we only get to spend so much time. So this was on the homework, but I don't think I really went over it in class so much. That made it a little harder problem. We don't cover it in class. And the other thing is your generation grew up without round clocks like we often have in some of the classrooms here. And the third problem was I think some people took the homework problem, which made it use the hour hand, and I did this one with the minute hand, and so they were off by a factor of 60 because they were doing how far the hour hand turned instead of. So all those things kind of combined to cause some difficulties on this problem. But the problem says this. The second hand this is a red herring here. The second hand begins on 12 and 2 minutes and 25 seconds pass. What angle has the minute hand swept through in degrees? And it doesn't matter where the second hand starts, you can just drop that off. That's what we call a red herring in this country. It means it doesn't have anything to do with the problem. But it was also on the homework. It didn't matter what it was there, even though I think it was the same hand. What angle does the, it's when the minute hand sweep out? I did this with the second hand. Maybe that's the trouble. Sweep out. Yeah, maybe you asked this because I think there's an error on the key here. I was doing the minute hand, not the second hand. So if you have, what I had here was 2 rotations plus 25/60ths of rotation, right? There's 60 seconds, 60 minutes in an hour, 60 seconds in a minute if I was doing the minute hand. 2 rotations plus 25/60ths rotation was how far the second hand went. And then it's minus because it's clockwise, right? Clockwise is a negative angle. So this is what I put on the key here, which is online, I think. It's minus 145 1/60th of a rotation. This was the second hand. Now the minute hand is gonna go 1/60th that far, so the actual question was the minute hand is minus 145 over 60 squared, right? Over 60 times 60. $2,600 rotations. Then if that's the minute hand, I want to convert that to degrees. The degrees for that be minus 145 over 3,600 rotations, right? That's what we got here, times 360 degrees for every one rotation. Rotations cancel. You get the number of degrees. Let's see what that comes out then. 5 times 360. Well, divided by 3,600 is pretty easy. 600. Gives us 14.5. Apparently it goes through 14.5 degrees. And what I put on the key, I marked it right if you did the minute hand. It should have been, I think on the key I put times 60. It was 870 degrees. But there's how far the minute hand moves, or minus 870 degrees, second hand. Well, I graded it this way in the second hand, but then it switched to minute hand in the middle. Sorry about that. And if you put 14.5, come see me after we. Probably right. I got it right. All right. So, I'll take either one of those answers. Either how far the minute hand went, or how far the second. Any others? But it doesn't matter in either case where the second hand begins or when the other hand begins. It's just how far it slipped out. Okay, I'll leave it there then. Feel free to come ask me after class or at the office hour I have down the hall at the end. Or if I miss out of your score, certainly come see me. You got over 100, you still get to add them up. Got low, don't worry too much. Be very careful to do much better in the next test, but remember we are dropping the lowest score. So if you just had a bad test and you're sure you can do better in the next test, then it won't. Yeah.
Points, how much is it?
Oh, there's 120 some points possible, but I'll just, you could get if you didn't miss anything, but I'll just grade it on a 90, 80, 70 scale. Well, today we want to continue on inverse trig functions. And he said last time we could do inverse sine like this. If you want an inverse of any function, you flip it over the line y equals x. Right? And so here's the sine. It's going. And we can't find an inverse for this one because an inverse that's a function for this one because horizontal line through here intersects an infinite number of times, the inverse won't be a function. What we do is we take this piece of the sine function So y equals sine x. And if we take this piece and try and find the inverse, which from algebra, you get it by flipping it over the line y equals x. Here's y equals sine x. Flipping this over the line y equals x to get its inverse, just like you did in algebra with exponentials and logarithms, gives you this function here. That's the inverse of the sine function, just this piece. We should draw it in a different color here. Let's do that. So from the inverse, or from the sine function, we flip over this line, y equals x, that splits the quadrant in half. And get this one. Now the sine function, we know that the sine of pi over 2 is 1. So it has that point. Consequently, when we flip this over the line y equals x to get its inverse, it has the point 1 pi over 2. Right? And this one, the sine of minus pi over 2 minus 1, circle. And when we reverse those coordinates and find on the inverse function, we get the point minus 1 minus pi over 2. And then 0, 0 reversed gives us 0, 0. So that's an important point. This is called the inverse sine function, but actually it's only the inverse of this piece of the sine function. It also has the name arc sine. It means exactly the same thing. But because no vertical line intersects it, or because no horizontal line intersected this piece more than once, now no vertical line will intersect this more than once. This curve here, which actually has equation x equals sine y, makes y a function of x, and so we just call it this name, y equals arc sine x. And then we don't need this notation anymore. So that's how it's defined. And then when you look at it, you find out its domain, the set of all x values you can put into it and get out a y value, is minus 1 less than or equal to x less than or equal to 1. Right? Because the smallest x value is minus 1, the biggest x value is plus 1. The range, the set of all y values you can get out, we said, minus pi over 2 to pi over 2. That smallest y was minus pi over 2, largest one, which means the arc sine can only give you angles in the first or fourth quadrants between plus and minus 90 degrees, minus pi over 2 and pi over 2. Mostly we'll graph these in radians. That's where the applications are. You can do it in degrees in your calculator. If it's in degrees mode, we'll calculate the arc sine in degrees, or if it's in radians mode, we'll calculate in radians. Make sure it's in the right mode for the test. But this is its graph when you put it in radians. And it has this important property. Because inverse functions have this property, f inverse of f of x gives you x back for any x. Consequently, the inverse sine of the sine of x, f inverse of f of x, has to give you x back also. However, unfortunately, not for all x. Why not for all x? Doesn't it give you x back like the general inverse function does? Because we only took a piece of the sine function, right? It will only give the arc sine is actually not the inverse of the whole sine function. It's only the inverse of this piece of the sine function. So it only gives you back x if you start on that piece, minus pi over 2 less than or equal to x less than or equal to pi over 2, first or fourth quadrants. And it gives you something else otherwise, which we will discuss what it gives you later. Okay. So the inverse property works that f inverse of f of x is x, but only for the piece we use. And then the other order should also work, right? For inverse functions, it's also supposed to be the case that f of f inverse of x gives you x back. Said. So we should have sine of inverse sine of x is equal to x always for all x in the domain. And in fact, we do. However, even though it always works for all x in the domain of the arc sine is only minus 1 to 1. Those are the only x coordinates you have. So we'll put this disclaimer on it. The function is only defined for x between minus 1 and 1. Undefined otherwise. So those were the properties of the inverse sine function. I hope this isn't too much review, but I think it's kind of important. And now you could use the unit circle to evaluate some inverse sine functions. So when x sine special angle multiple of pi over 6 or pi over 4 we can evaluate the arc sine of x by hand exactly. It is a nice special angle. So there was some examples of that. Any questions in all this so far, what we did to get this? All right. I could ask you, what is the inverse sine minus square root 3 over 2? I'll do a harder one here. What is that? Because we're doing the inverse problem, when you do the sine of an angle, you're saying, what is the sine of that angle? But the inverse sine going backwards is saying, what angle has that sine? So that's the question you ask to compute an inverse sine. What angle theta in space has sine equal to the given number? But it's more complicated than that. There's an infinite number of answers to this, but the arc sine gives you the angle between minus pi over 2 and pi over 2. Those are the only angles it can output. So that's the question when you want to evaluate an arc sine exactly by hand. So for this one, for these, we can use the unit circle. And in fact, you get to where you can just sort of imagine this in your mind. Sine theta is the y coordinate on the unit circle. So I'll draw all y coordinates minus square root 3 over 2. All right, here's minus 1 down here. And when I sketch that, I observe there's only 2 points on the unit circle where the y coordinate is minus square root 3 over 2. So there's only 2 possible terminal rays, that one or that one. And I need an angle theta that gives those terminal rays. Well, there's an infinite number of angles. I can go out any number of times and wind at either one of those. But there's only one angle between minus pi over 2 and pi over 2, and that's the arc sine. The arc sine is a function. It outputs only one number when you give it a number, and it's the angle between here and here, right? Minus 90 and plus 90 if it has the sine. So I throw out that one, it's the wrong quadrant, and I don't go around this way, I go around this way. Get an angle between plus and minus pi over 2. What's that angle? Well, you drop the perpendicular and figure it out. And you say, since this goes down to minus square root 3 over 2, the side length must be plus square root 3 over 2. This is 1 because it's a unit circle, and that forces by the Pythagorean theorem this to be a half. I know that just by memory that it's going to be a half. And this angle, consequently, is going to be pi over 3. Since I go in this direction, we call it minus pi over 3. So there's the answer. The arc sine of minus square root 3 over 2 is minus pi over 3, exactly. All right? Pi having a decimal that goes on forever without a repeating pattern. If you do a calculator approximation, it will be not exact. Yeah.
Why is it quadrant 3 instead of,
Quadrant 4, yeah.
so why is it quadrant 4?
Oh, and not quadrant 3, yeah.
Yes.
Because the arc sine is the unique angle between plus and minus pi over 2. Minus pi over 2 here and plus pi over 2 up here. It's just the way we define it. So it always gives you an angle in one of these two quadrants. So that's how you find the arc sine of any angle. And then Other arc sine values are found by calculator. It's not from, if it doesn't give you a special angle as an output, then you have to use your calculator. So you look at it and say, does that number look like a square root 2/2, or a square root 3/2, or a 1/2, or a 1, or a 0? Then it comes from a special angle, and you can do it, and otherwise you just can't. So here's another example. Suppose I told you find the arc sine of 1.1. What's the answer there? Undefined, right? The domain is -1 to 1. If you put in any other number, your calculator will tell you domain error. Oh, what's ERR or ERRO or something like that. Meaning you can't take, this is asking the question, when is the sine equal to 1.1? It's never equal to 1.1, right? It oscillates up and down between plus and minus 1. And so the sine is never equal to 1 at 1.1. Never gets that high. So this is asking a nonsense question. And of course it says domain error. Okay, now the object is to do the same for inverse cosine and inverse tangent. And the good news is we're not going to do the last three. They do exist, but they're seldom used because almost all problems you can solve with those three, you can solve with these three, and you just don't need them. So almost all trig books just don't cover them, but you can look online for a Wikipedia page up here, maybe I'll put up in a minute, and you can see what they look like, but nobody uses them. So now the second thing, that was arc sine, is inverse cosine. A very important problem in lots of things. We already saw with triangles before. Sometimes you need to know what angle has that cosine in order to solve the triangle, right? So we actually have used this already. There's lots of applications where you need solving a triangle with them. How can we find that? We can do exactly the same thing. I look at the cosine wave, a cosine function, which is a sine wave, and it looks like this. And I notice immediately I've got the same problem. Here's a horizontal line that intersects us an infinite number of times, right? So if I find the inverse relation to this function, it won't be a function, right? It'll, if I take and flip it over the line y equals x to interchange the axes, it'll wind up like this along the axis and be a multi-valued function, we call it. For any x, there'll be this value y, this value, this y. So the inverse of the cosine function is not a function, it's just a relation. It's a multi-valued function. We want to take a piece of this one that no horizontal line intersects more than once. And alas, I can't do it about the origin like I did with sine, because no matter how small a piece I take, a horizontal line intersects it more than once. So that's no good either. Instead, I'll start at the origin and move to the right and take this piece of the cosine function. Here down to here. Or this is pi, if you recall. Cosine of pi is -1. So now I'll flip that one over the line y equals x. Let's draw it here. The point right here, cosine of 0 is 1, so this is the point 0, 1. Cosine of pi is -1, so this is point pi -1 on the function y equals cosine x. The inverse is gotten by interchanging x and y, right? The inverse relation is x equals cosine y. Okay. You flip it over this line, and now you get this function. Instead of starting at 0, 1, it starts at 1, 0, because you just interchanged x and y. And this goes up like this. And this one reverse gives you -1 pi is the point here. And this important point here, halfway in between, all that the cosine of pi over 2 is 0. You can get that from the unit circle. Means that this point here, the y-intercept on this function is going to be 0 pi over 2. this one is called the inverse cosine of x, or equivalently, arc cosine of x. That's the one that undoes the cosine. Since we got it as the inverse function, it's going to undo the cosine. We have these properties. Once again, the smallest x coordinate is -1 and the largest is 1. So the properties include that the domain is -1 to 1, just like the arc sine. Numbers you can put in and say, what has that cosine? But the range is different, right? All the y values here, the smallest y value is 0 and the largest y value is pi. So it's 0 less than or equal to y less than or equal to pi is the range. It's an inverse function, so it's supposed to be that cosine inverse of cosine of x should give you x back, right? And it does if it's a true inverse of the whole function, except it's not a true inverse of the whole function, right? It's only an inverse of this piece. X equals 0 to x equals pi. Since it's only inverse of this piece, it only inverts it if x is between 0 and pi. Right? And it will give you something else that we'll discuss later otherwise. So there's the inverse property for the piece that we inverted. The other one direction, since the inverse cosine, the whole thing is a piece of the cosine function, the cosine will always invert the inverse cosine. It'll always give you x back. But it's only defined for x between -1 and 1. And otherwise it's undefined. If x is less than -1 or greater than 1, you'll get a domain error on your calculator. All right, so there's the properties. I hate to get rid of the sketch, but you can find other points on this thing too. We mentioned that with sine. How can I find another point on it? For instance, if I took a special angle here, pi over 3, what's the cosine of pi over 3? I recall it's a half. So the point pi over 3, a half is on the cosine function. It follows that the reverse pair, 1/2 pi over 3 is on the inverse cosine function. So you can do all of those like that, but those are not so important. Just these 3 points are really important. So let's calculate some examples by hand. Find inverse cosine of x by hand exactly when a special angle results. So you look to see if it's a special number going in. We're taking the arc cosine of a number that we recognize coming from a special angle, such as -1 over square root 2, then we can do it exactly. How do I know -1 over square root 2 is the cosine of a special angle? Slightly tricky. Because if you rationalize it, it's also minus square root 2 over 2. Oh yeah, when I take the cosine of a certain angle, I know I get minus square root 2 over 2 exactly. What angle could that be? Well, the arc cosine again is the reverse question. Since it's an inverse function, instead of saying what's the cosine of the angle, you're saying what angle has that cosine? What theta has cosine theta equal to a given number -1 over square root 2? Now, the trick is that the output it gives you is not the angle of first or fourth quadrants, but the first or second quadrants for our cosine, right? It gives you an angle between 0 and pi. So the question is what angle this time between 0 and pi has the given cosine? Once again, you can go to the unit circle as a nice way to do it. This time, since we're doing cosine, we're saying x coordinate has to be this number. So we plot all the points, x equals minus 1 over square root of 2. That's something like that, minus 1.7. Say, we need a point on the unit circle with this x coordinate, so there's 2 points, and hence only 2 terminal rays possible to give cosine equal to minus 1 over square root of 2. So far. Now, which one do we want? Well, it has to be first or second quadrant, angle from 0 to pi. It has to be this angle right here, to be between 0 and pi, right? So it's out, it's the wrong quadrant. Can't go this way, that's a negative angle. Pi. All right, so what angle is that? Well, we know that this goes over to minus square root 2, so this side length, 1 over square root 2. So this side length must be plus 1 over square root 2. This is 1 for a unit circle. It follows by the Pythagorean theorem, if you calculate it, this must also be 1 over square root 2. And we recognize a 45, 45, 90 triangle. Once you know this side is square root 2 over 2, and this side is 1, you know immediately that's a triangle you memorize, right? That's the 45, 45, 90 triangle. This angle must be pi over 4, the reference angle. That makes theta equal to pi back up pi over 4. 1 pi minus a quarter pi is 3/4 pi, right? 3 pi over 4. That's the angle. Maybe a difficult one here, right? But you start to be able to picture that in your head. In order to get the x coordinate to be minus 1 over square root 2 here, I'm going to have to come around 3/4 turn. That's 3 pi over 4. What's the arc cosine of 0? How about that one? Same thing. What theta between 0 and pi? This cosine. 0. That's what I'm going to put in the blank. There's only one answer to that. Arc cosine is a function, right? So I figured on the unit circle, cosine is the x coordinate. So I consider all points with x coordinate 0. That's the y-axis, right? There's 2 points in the unit circle right there and right there that have cosine equals 0. Only 2 terminal rays, this one and this one. This one is in the wrong place. It's not between 0 and pi. So it must be this one. Theta equals, oh, the y-axis is pi over 2. That's that one. The arc cosine of 0 is pi over 2. What kind of takes thinking backwards, right? What angle has that cosine? Then for non-special, or for x not from a special angle, my calculator get an approximation. Approximately get arc cosine of x. So if I want the inverse cosine, let's say of 0.1, not coming from a special angle, right? No angle I know of has cosine equal 0.1. Well, I'll just take second cosine, because remember from earlier in the semester, the inverse cosine is above. And be careful, some people think, oh, inverse cosine, that means 1 over cosine. It doesn't. It means the inverse function by flipping. This is not the secant up here. This is the inverse cosine, the one we get by flipping. It's just that conflict in notation, right? We said 2 to the minus 1 means 1 over the number, the multiplicative inverse. But a function of the minus one doesn't mean minus one power multiplicative inverse. It means the function gotten by flipping. This is the original function f of x. Means flip it over the line y equals x. It's a different concept. So this is not secant, it's inverse cosine that we want. So we'll take second cosine and then 0.1, parentheses automatically inserted. You may need to, depending on the calculator, close the parenthesis, however. PI84 automatically closes it. If you forget, it'll just put it in. Which can be bad if you forgot to put another one in earlier, put it in the wrong place, but for this computation, it won't matter. All right, and then push enter to evaluate it, and it will give you your number. So make sure it's in radians mode. All right, if you want the angle in radians, which is mostly what we want. I'll tell you on the test if I want degrees, but pretty much I just want radians. That's where the applications are again. All right, so my calculation of radians, and I'll just push second cosine 0.1. I'll hit the parentheses, it'll put it in. And I get 1.4706, blah, blah, blah. Is the inverse cosine of 0.1. So the inverse trig function is up above the corresponding trig function. You push the second key to invoke the, right, this might be blue on your calculator or yellow, and this will be the same colored letters up above the key. So this invokes the inverse cosine instead of the cosine when you push second first. Finally, we have the inverse tangent. Oh, and maybe I should show the picture of this real quick. See if I can get this to come up here. It's the wrong one. There we go. This is from Wikipedia. I just wanted to show you the official graphs. Online. Here's what they look like plotted by a computer. They're actually exactly the same shape, right? The sine and cosine are the same shape. So when I flip the sine over the line y equals x, I get this curve. When I flip the cosine, I get this curve. This one is actually just this one. If you flip it over and slide it up, they're exactly the same shape because they both come off of a sine wave. And they're both the same shape as part of a sine function, right? But there's the arc sine. You get put in a number between -1 and 1. You get, I'm sorry, arc cosine. Put in a number between -1 and 1, get out the cosine of the angle. And here's the arc sine. Put in a number between -1 and 1 and get an angle between -pi/2 and pi/2. All right. All right, arc tangent. What we can do for tangent is similar to what we did with the sine. Here is the arc tangent or the tangent function. It goes like this. It's a wiggle. It goes up to the origin, and it's at this inflection point when it shifts from being kind of bowl-shaped down to bowl-shaped up. Process here gives the x-asymptote, x-intercept. This asymptote is at -pi/2. This one is at pi/2. And that was y equals tangent x. And it repeats over and over with period pi. So it crosses here again at pi, crosses here again at -pi, we recall, right? And it has this nice point right here that the tangent of pi/4 is 1. And the tangent of -pi/4 is -1. It's an odd function after all. There's the tangent. So what can I do to find an inverse for this one? It fails the horizontal line check also. Right? It's a function because it passes a vertical line test. No vertical line intersects more than once. But because the horizontal line intersects more than once, it doesn't have an inverse that's a function. But what we can do is just take a piece of it and we'll do like the sine. We'll pick a piece as long as we can near the origin. And it'll be this one. And we'll flip this over the line y equals x. So here's the tangent function. These asymptotes. X equals minus pi over 2. X equals pi over 2. These important points, pi over 4, 1. Minus pi over 4 minus 1. And 0, 0. Everybody expects you to know those. We'll take that piece of the tangent only. X between minus pi over 2 and pi over 2. And we flip that over the line y equals x to get the inverse tangent. And right, if you think of flipping it like that, it looks like this. That's what we call the inverse tangent or arctangent. And it had vertical asymptotes at plus and minus pi over 2 for the tangent. When you flip it, they become horizontal lines. Y equals plus or minus pi. The arctangent has asymptotes, and it's actually exactly the same shape as the tangent. All you do is flip it. So the tangent rotated 90 degrees like that. There's what it looks like. And the nice thing has happened. What's the domain of the arctangent? This one. You can put in any x you want, right? If I put in this x, I get this y. Put in this x, I get one down here. Put in this x, I get this point here. It's defined for all x, so its domain is all real numbers. We put this capital R here. You bold these R in your book, which means minus infinity less than x less than infinity. All real numbers. The range, however, is not all real numbers. What's the range? I'll put y between these two asymptotes, right? So between minus pi over 2 and pi over 2, not including the asymptotes. So its range is like the sine, except without pi over 2 and minus pi over 2 themselves. So there's the domain and range of the arctangent function. And the arctangent is supposed to undo the tangent, right? But only on the piece that we used, which is here, angles between minus pi over 2 and pi over 2. So that's where it works. Arctangent of the tangent gives you x back only from that piece. X between minus pi over 2 and pi over 2. But, well, it gives you something else otherwise. This whole arctangent is part of the tangent, and so the tangent always inverts it. The arctangent of x always gives x back. It doesn't matter what x you put in. It's defined for all x, and the whole thing flipped as part of the tangent function. It always gives you x back. So this is a nice, easy one. Tangent of the arctangent always gives you x back. Just like the arc sine and arc cosine, we want to be able to find some arctangent values exactly. The ones you can memorize are these corresponding points here, right? If minus pi over 4 minus 1 is on the tangent, minus 1 minus pi over 4 is on the arctangent. Pi over 4, 1 is here. 1 pi over 4 is on the arctangent. A couple extra points you can do that. For example, to say I want to solve inverse tangent of minus square root 3. How do I do that one? Again, I asked the reverse question. Since this looks like it came from a special angle, I'm going to try and do it by hand. I'm going to say what theta in the range of the arctangent between minus pi over 2 and pi over 2, not including the endpoints like sine did, has this tangent. How about that? Once again, just like the other ones, we use the unit circle, but remember tangent and cotangent are actually the hard case. We can rewrite this as minus square root 3 over 1, right? That's the same thing. And then to get a corresponding point on the unit circle, divide top and bottom by the root sum squared, right? Minus square root 3 squared plus 1 squared, and square root 4 is 2. I write that as minus square root 3 over 2 over a half. Oh yeah, of course, those look like points, a point on the unit circle, right? So it could be that point, but there's another point it could be also. That's where this 2 comes from. This will be 1 point on the unit circle, but the alternative is instead of dividing top and bottom by 2, you can also divide it by minus 2 and get square root 3 over 2 over minus a half. This is a y and an x on the unit circle also. So it's one of those 2 points. Which one is it? Has to give me an angle in the first or second quadrant, like arc sine. So I can take this one, minus square root 3 over 2 and 1/2. That'll be in the second quadrant, that works. The other one over here, minus a half plus square root 3 over 2 is in the wrong quadrant. Throw this one out, say this one is in the right quadrant. Now what angle is that? If I go a half this way and square root 3 over 2 this way, then this little special triangle here must have an angle pi over 3, and going clockwise, this is minus pi over 3. Fit the pi over 3 angle within the triangle. We make triangle angles positive. So we're rotating plane clockwise, we call it minus that angle. So this one is minus pi over 3. How about that? But you start to be able to picture it. If you just think, oh, minus square root 3 over 2 over a half. So that's y and x. I'll go over a half and down square root 3 over 2. That's a 60-degree angle that way. Minus 60 degrees. Minus 60 degrees. They're solving the arctangent problem. Now, one last thing, if I have time, I think. We want to be able to evaluate the inverse trig functions at special angles and be able to use a calculator to approximate it in other cases, but a real significant application comes up in calculus that you see fairly frequently and lots of other high mathematics, is this. When trig function of an inverse trig function, not the other way, not inverse trig of trig, but a trig function of an inverse trig function is evaluated, it can always be done by hand. It doesn't have to be a special angle anymore. How about that? Can done by hand exactly for any angle. How about that? And amazingly, it comes out to be an algebraic expression. It's not only can it be done, but it's algebra. It comes out with square roots and that kind of thing. All the trig functions go away. And the method is this. I think you just, rather than spell it out in detail, I'll show you by example. You do it, it is done by a right triangle with an angle theta equal the inverse trig function that appears. If you just remember to draw that, you can figure the rest out. So I'm going to try this example here. What is the tangent of the inverse sine of 0.1? How about that? 0.1 isn't the sine of a special angle. I don't know how to find the arc sine of that exactly. How am I ever going to find the tangent of an angle? Can't even find it exactly. Well, your calculator can do this too if you bought one of the advanced calculators for the math majors and physics majors, engineers. But you can do this by hand. Here's what we can do. Step one, you sketch a right triangle with the inverse trig function you see. That is theta equal the arc sine of 0.1 in this case. Any right triangle such that that's the case. Equivalently, since it's a right triangle, this is sine theta equals 0.1. In a right triangle, these two are equivalent. So I draw a right triangle. Doesn't even have to be to scale very well. I call this theta, and this won't be to scale. And I can put opposite over hypotenuse equal to 0.1, so I can put 0.1 here and 1 here. And that works, but I'm going to suggest you don't do that. What would be better than putting 0.1 and 1? All right, so the sine opposite over hypotenuse is 0.1. I can scale this any way I want. I could call this 1 and this 10, right? I could think of this as 1/10. Then I can use whole numbers. So you don't have to use whole numbers. It will work always, but whole numbers are easier, right? So I'll put it as 1/10. Now, the second one is to get the last side by the Pythagorean theorem. Got two sides of a right triangle. This always works to find the last side. What is the last side? Well, it's a leg, so it's square root hypotenuse squared minus leg squared. Pythagorean theorem solved for the last leg is square root of 10 squared minus 1 squared. Right, is the square root of 99. Or, right, this is 9 times 11. So we could call this 3 square root 11. All right, so there's that side. And now you just evaluate the trig function using the triangle. But it's just 1, 2, 3 every time. Construct the right triangle. Find the last side by with the inverse trig function that appears. Find the last side by the Pythagorean theorem, and then use the triangle to evaluate it. If you get a negative in here, there is one more thing to say. So we'll do that if we have time with one more example. All right, so what I want is the tangent arc sine 0.1. Oh, the arc sine of 0.1 is theta in the triangle, so this is tangent of theta. But tangent of theta is the opposite side over the adjacent, right? So it's 1 over square root 99. 3 square root 11, let's call it. There it is. There's the tangent of the arc sine of 0.1 is 1 over 3 square root 11. Exactly. And you notice it comes out to be an algebraic expression. What's really neat about this is you can do it even if you have a variable in here. It shows that you can do it for any angle. Well, let's try one more first because I want to do a a special case. What if I wanted the cosine of the arc sine of 1/3? How about that? 1/3 isn't the sine of a special angle, so I can't do the arc sine exactly. Nonetheless, the trig function of the inverse trig function can be done exactly. Just remember that. Trig function, inverse trig function, draw a triangle, right? So step one, I draw a triangle with theta equal the arc sine of 1/3. Since this is a fraction, let's rewrite it as sine theta equals 1/3. In fact, I'm going to do one more thing. Let's not make it 1/3. Let's make it minus 1/3. Let's make it harder. What am I going to do with, now I can't put a negative side on a triangle. What am I going to do? I meant to do this. Here's what you can do in almost all cases. We'll have to do one more next time, is you can use the even and odd properties. If you remember the graph of arc sine, it's an odd function, right? It's symmetric. So it's an odd function. We can pull the minus sign out. Arc sine of minus x is minus the arc sine of x. It's an odd function like sine is. In fact, the inverse of any odd function is always an odd function. So it doesn't work with even functions. Be careful, but the arc sine and the arc tangent are both odd because their original functions are odd. So we know this property. We can pull the minus out and say this is also the cosine of minus the arc sine of plus 1/3. Pull the minus out, it's an odd function. And now cosine of minus this one is what? Is the even property of cosine, and the minus goes away. Right? Because cosine of minus x is cosine plus x. It's an even function. So even and odd properties, you can almost always do this. One more case to consider, but now I can just draw this triangle. One, I look for theta equals the arc sine of 1/3, like we suggested, which means I draw a triangle with opposite over hypotenuse 1 to 3. We'll just pick the obvious thing, 1 here and 3 here. Easiest way to do it. 2, Pythagorean theorem to find the last side says, what is this side? Square root of 3 squared minus 1 squared. Right, is square root of 8. 2 square root 2 when I simplify it. 3. What's the, I'll use this one. Well, the cosine of the arc sine of minus 1/3. Also, from this one, the cosine of the arc sine of plus 1/3. That I just calculated. But arc sine of 1/3 is theta. That's the way we constructed the triangle. So it's cosine theta, which is adjacent over hypotenuse, which is 2 square root 2 over 3. So there's that one exactly. You make theta the angle in a right triangle corresponding to this inverse trig function. Finish with the Pythagorean theorem. Evaluate it using the triangle. On the homework, try these. 6.3. Let's see. Put the 4 for right now, and we'll have to do the other order, inverse trig of trig functions next time. Those would be good to practice for next time.